Hi everybody, Mrs. Pesic here. This is our look at section 4.4, properties of logarithms, and also one last look at section 4.3, logarithm functions continued, because on the video that you saw just previously, there was no graphing of logarithms, but we do need to talk about that. So let's start with that first. We're going to look at graphing. So this is really section 4.3. Continued, and we're going to talk about how to graph the logarithmic functions. So, for example, let's say we wanted to graph f of x equaling 3 to the x. I know that's not a logarithmic function, but it is it is an exponential function. We've done some like this, so I know that you know that if we plug in -2 in for x right here, we would get 3 to the -2, which is 1 over 3 squared, which is 1/9. So I can put 1/9 right there. If I plug in -1, I would get 1 over 3 to the positive 1. That's going to be 1/3. If I plug in 0, 3 to the 0 is equal to 1. If I plug in 1, I get 3 to the first is 3, and 3 to the second is 9. So if I'm going to graph those, points, here's -2 is at 1/9. -1 is just a smidge higher at 1/3. 0 is here at 1. 1 is at 3, and 2 is at 9. So it is rising very rapidly. So our graph is an exponential growth function, and it would look something like this. So what's the domain? The domain for this graph would be all real numbers. Plug in anything you want. So we can write that as -infinity to +infinity, all real numbers. The range, however, is just going to be the positive y values. So we can say we want to go from, I was going to say 0 to +infinity like that, but that would actually include 0. We don't want to do that. So let's make this a parentheses here, and we would say 0 to +infinity. Remember, that's the same as saying y is greater than 0. All right, that's the domain and range for f of x equaling 3 to the x. All right. But what if we were going to graph its inverse? Remember, to graph its inverse, we would take all of these ordered pairs and we would reverse the x and the y. So if we wanted f inverse of x versus x, we would have 1/9 going to -2, 1/3 going to -1, 1 going to 0, 3 going to 1, 9 going to 2. If I graph those, 1/9 goes to -2, so that's about here. 1/3 goes to -1, so that's about here. 1/0 is here. I hope you're graphing this on graph paper with me. 3 goes to 1, and 9 goes to 2. So this is the inverse of f of x equaling 3 to the x. The graph looks something like this. All right, where this graph here had a horizontal asymptote, our original function had a horizontal asymptote of y equals 0, this new graph is actually going to have a vertical asymptote. That's this line right here, and that is the equation. Asymptote, let me spell that out. Vertical asymptote would be x equals 0 for this. This function right here is a logarithmic function. It would be f of x equaling log to the base 3 of x. That's really what we just graphed. And just to test a few points there, if that really is our function, if f inverse of x is equal to log to the base 3 of x, and I could have called this f inverse of x, is log to the base 3 of x, then if I was to plug in, for example, 3, what's log to the base 3 of 3? I'm plugging this 3 in right here, and this is saying what number do I, if I take 3 raised to what power will I get 3? And the answer is 1, so it does work. All right, so that's how to graph an inverse of an exponential function. In other words, that's how to graph a logarithmic function. Logarithmic functions will always have a vertical asymptote. Exponential functions always have a horizontal asymptote. All right, so that is the example from section 4.3 that I wanted to cover. And now we're ready to move on to section 4.4. So in section 4.4, these are called properties of logarithms. There's lots of interesting examples that you can talk about with logarithms. I even mentioned the earthquake example. And so let's take a look at the product property of logarithms. So the product property of logarithms, if we were to write out the product property would look like this. It is the logarithm of a product is equal to the sum of the logarithm of its factors. And that in symbols, it would look like this. Log to the base b of m times n is equal to log to the base b of m plus log to the base b of n. And this might seem a little surprising because we're multiplying over here, and over here we're adding. You might think that it should be log to the base m of m times n is equal to log to the base b of m times log to the base b of n. But that is not true. We don't want a multiplication here. We want addition. All right, so let's take a look at an example of this product property of logarithms. So, is it true that log to the base 2 of 8 times 4 is equal to log to the base 2 of 8 plus log to the base 2 of 4? Because that's what the product property of logarithms is saying. Let's actually evaluate both sides separately and see if it really works out to be true. So 8 times 4 is 32. So on this side, we're evaluating log to the base 2 of 32. Well, remember what that's saying. That's saying 2 raised to what power is going to give me 32. That's what this is saying. And so the answer to that is 5. 2 to the 5th is equal to 32. So our left side of our equation is actually equal to 5. What about over here? What's log to the base 2 of 8? If we're trying to find this, that's saying 2 raised to what power gives me 8. And the answer to that is 3. 2 to the 3rd is equal to 8. So this one right here is 3. Here's my plus. And then what about over here? Log to the base 2 of 4. That's saying 2 raised to what power gives me 4. Well, the answer to that would be 2. 2 squared is equal to 4. So this is equal to 2, and 3 plus 2 is 5. So we do get a true equation, 5 equals 5. So this is a true statement here. And this is an example of the product property of logarithms. All right, so on this example, express log to the base 6 of 4 plus log to the base 6 of 9 as a single logarithm, and then simplify if possible. So let's try this one. This would be using our product property of logarithms. This is the same thing as saying log to the base 6 of, is it 4 plus 9? Or is it log to the base 6 of 4 times 9? I'll give you a multiple choice here. Is it A or is it B? Well, I hope you chose B. This is correct. We don't want to do this. Yes, there's addition here, but there's got to be multiplication here. So this is really the same as saying log to the base 6 of 4 times 9, which is 36. All right. And can we simplify that answer? Well, this is saying 6 raised to what power is equal to 36? Well, I hope that you're telling me that what's in the box should be 2, because 6 squared is equal to 36. So our answer to this right here, this is really a fancy way of writing 2. All right, let's take a look at the quotient property of logarithms. This is similar to the product property, but the quotient property says the logarithm of a quotient is the logarithm of the dividend minus the logarithm of the divisor. Lots of words. Let's take a look at the symbols. It's really log to the base log to the base b of m over n is going to be equal to log to the base b of m minus log to the base b of n. Notice if you are dividing here, there's our division symbol, you're going to want to subtract when you pull the two logarithms apart. So let's take a look at this example. Let's test this one. Is log to the base 2 of 30 over 6 equal to log to the base 2 of 30 minus log to the base 2 of 6? Let's test this by evaluating both sides. Well, over here on the left side, we would have log to the base 2 of 30 over 6 is 5. That's log to the base 2 of 5. And over here, we would have log to the base 2 of 30 minus log to the base 2 of 6. Log to the base 2 of 30 minus log to the base 2 of 6. I didn't really do anything to simplify that. But let's check this on our calculator to see if this is accurate. If I do log to the base 2 of 30 over 6, that's log to the base 2 of 5. Let me get to a new calculator page. To get logarithms on your calculator, you see the log button is over here. You want to do Control log here, and it's asking you what base you want. And in our example, we wanted base 2, so I'm going to type in a 2 there. Right click gets me here, and I wanted 30 divided by 6 is 5. So I want 5 here. This is really saying 2 raised to what power would get me 5? And the answer is about 2.32. All right, but what about the right side of this equation? I had log to the base 2 of 30 minus log to the base 2 of 6. So let's see what that is. Log to the base 2 of 30, I go Control 10 to the x, that's log, I want to the base 2 of 30, okay, and then right click to get out of that parentheses, I want a minus, and then log to the base 2 of 6, and let's see what that equals. Log to the base 2 of 30 minus log to the base 2 of 6. There it is, 2.32193, same as before. So the quotient property does work. All right, and let's try this last example for the quotient property. Express log to the base 5 of 100 minus log to the base 5 of 4 as a single logarithm. Notice we're subtracting two logs with the same base. They have to have the same base. That means we can rewrite it as a one logarithm with a quotient. So this would be log to the base 5 of 100 divided by 4. That's log to the base 5 of 25. And if we can simplify that, we should. This is really saying 5 raised to what power is equal to 25? Well, that would have to be 2. So our answer here is 2. So this is equal to 2. Okay, then that brings up the power property of logarithms, which basically says that the logarithm of a power is the product of the exponent and the logarithm of the base. So written out in symbols would look like this. Log to the base b of a raised to the p power would be the same as bringing this exponent down in front and rewriting it as p times log to the base b of a. So, for example, express as a product, simplify if possible. So we have log to the base 4 of 4 raised to the 20th. Remember, if you have base 4 of something raised to a power, this exponent can come down in front. So this is really going to be equal to 20 times log to the base 4 of 4. So that exponent is gone, it's been brought down in front. So we end up getting 20 times log to the base 4 of 4. But log to the base 4 of 4, that's really saying 4 raised to what power gives you 4? Well, what should that be? Well, that should be 1. So we really end up getting 20 times 1, and we get 20 as our answer. And here is a notes must do for you. Express as a product and then simplify if possible. Log to the base 2 of 32 raised to the 6th. So that's going to be very similar to what we just did here. Please make sure you write notes must do on your notes, and pause this video and try this one, and then resume for the rest of the video. Okay, so that leads us to inverse properties of logarithms and exponents. Log to the base b of b raised to the x is just going to be equal to x. Here's an example. Log to the base 6 of 6 to the 5th is just going to be 5. And let's take a look at that for a minute before we look at the other inverse property. So why is it just going to be 5? Well, from the property we just looked at, this 5 can come down in front, so we'd have 5 times log to the base 6 of 6, but log to the base 6 of 6, as we just saw, that's equal to 1. So that's why this is going to be equal to 5. What's the other inverse property? It says b raised to the log to the base b of x is equal to x. And here's an example. 4 raised to the log to the base 4 of 3 is equal to 3. All right? So those are the inverse properties of logarithms. And we've got one example, one real-world example about earthquakes to look at. Seismologists use the Richter scale to express the energy or magnitude of an earthquake. The Richter magnitude of an earthquake, we're going to use M to represent the magnitude in the Richter scale, is related to the energy released by the earthquake. And we measure the energy in ergs, which we use E for. And here's the formula for it. M equals 2/3 times log of E divided by 10 to the, that's supposed to say 11.8. I hope you can read that okay. All right, so the tsunami that devastated parts of Asia in December 2004 was spawned by an earthquake with a magnitude 9.3, which is really very high magnitude for an earthquake. So find the energy released by this earthquake. So in order to do this, we would plug in 9.3 for M for the magnitude. That's going to go in right here. So we're going to have 9.3 equaling 2/3 times the log of E over 10 to the 11.8. And to solve this equation, we would want to multiply both sides first by 3/2. All right, that will get rid of the 2/3. So 3/2 times 9.3 on my calculator. 3/2 is 1.5 times 9.3, and I'm getting 13.95. And that's equal to log of E over 10 to the 11.8. Well, remember the properties of logarithms. If you're dividing here in one logarithm, we can split it up and write it as 2 separate logarithms with a subtraction between. All right, and one thing that we probably didn't talk about, I don't know if you noticed this, but there's no base here. There was no base written. No base here. There was no base written here. Well, if there's no base written, it's understood to be base 10, and we call it a common log. Our common log means base 10. All right, so that can help us with this. So we have now 13.95 is equal to log to the base 10 of E and minus log to the base 10 of 11.8. So let's do this. Let's bring this 11.8 down in front, and we'll have 13.95 equaling log to the base E minus 11.8 times log 10. All right, and then what is log 10? Remember, this is really base 10. So 10 raised to what power gives me 10? That's going to just be 1. So I get 13.95 equaling log E minus 11.8 times 1. and I can subtract, no, add 11.8 to both sides of the equation, and 13.95 plus 11.8 oh boy, 13.95 plus 11.8, I'm getting 25.75 equals log of E, and now we need to solve for E. So in order to do that, keep in mind that this is base 10, so this is really log to the base 10 of E equaling 25.75. And if we're trying to solve for this mystery energy level, E, in ergs, we're going to rewrite this so it's in exponential form. This is currently written in logarithmic form, but if we want to rewrite it in exponential form, that would be saying what base raised to what power equals what. Remember, we did this on the last video. So the base is 10 raised to, remember, logarithms are exponents, and 25.75 is the logarithm, so that means that's the exponent, equals E. So the energy level is going to be 10 raised to the 25.75. Let's see if our calculator can even handle something like that. 10 raised to the 25.75. I'm getting 5.6 times 10 to the 25th. 5.6 times 10 to the 25th is my energy level. All right, and that is in ergs. All right, so that finishes up this video. Thanks for watching. Hope you took good notes. Hope you did those notes must do, and that you have the first videos, video guided notes completed as well. All right, have a good day. Thank you.